Hey, welcome back to Bennett's Chemistry 12 tutorials. We are on to, we're on to episode 22 here. And in this episode, we're continuing with the work that we've been doing on titration. So we're going to kind of cut to the chase and just get into calculations that are associated with titration. Previous videos on titration all go into the theory and the use of the actual equipment and some of the subtleties and the indicators and technique-wise and things of that nature, all kind of embedded into what I've done in the previous videos. So if you're looking more for what would it look like if you were in the process of doing the titration in terms of technique and setting the thing up and the theories behind the indicator choice and all that kind of stuff, the previous videos will do all of that. This one's going to be, I'm going to make the assumption on this one that you already know how to set the thing up and do the titration and what it means to get to equivalence and all that kind of stuff. Okay, so now this is going to be, okay, so if you do a titration, you do it properly and you get the information from it. From the practical side of things, how do you do the calculations? How are titrations useful for actually understanding different bits of information about the unknowns that you're actually titrating? Okay, so I'm going to do two problems today, and the first problem is going to be calculating the Ka of a weak acid, which I'm going to do an example that's a weak acid, but of course you could do the Kb of a weak base as well. The technique would be exactly the same. There'd be some subtleties, obviously, because one's a base and one would be an acid, so what you're titrating with, what initial pH is going to tell you. Some subtle differences in there, but the plan of attack would be the same for both. And then the second one I'm going to do is a percent purity, which is it's a commonly used titration. Is a commonly used technique to find out the percent purity of something, because you do have such finite control of how much reactant you add into something. Okay, so let's jump right in there. So the first one, calculating the Ka. So you might get a scenario such as this. Perhaps you're given a lab scenario where you have to do this, or it's just pen and paper, a question that you're asked to do. So I've written the whole question up here on the board, so I'll read it in case it's a little fuzzy, in case the clarity isn't there. So the question says, an unknown weak monoprotic acid, HX, is titrated using 0.150 molar NaOH in order to determine its Ka. If the HX solution had a pH of 3.80, use the titration data to calculate the Ka of HX. So there's a few things that are kind of tied in there. Number one, it's important that you know that it's a weak monoprotic thing, because that's going to tell you something about the stoichiometry of the neutralization. It's telling you it's weak, obviously, which you wouldn't have a Ka if it wasn't weak. It's also telling you what the pH is. And a word that isn't used in there that I could have added quite easily is titrated using standardized 0.150 molar NaOH. The word standardized means known concentration. Okay, and there's a process to being able to have a solution of known concentration. Again, it's in the previous videos kind of embedded in there. I've talked about standardized solutions. So we're going to assume that the sodium hydroxide is standardized. So how do you do this? So it tells you an initial pH. You have to understand, to be able to calculate a Ka of something, what you need to do is you need to be thinking IRE table. Okay, so what I'm going to do is right underneath here, I'm going to draw an IRE table just to kind of demonstrate what the plan of attack is going to be. So if I had a weak acid HX, okay, so there's an IRE table for HX, if HX was sitting in water. Now imagine this solution of HX before you do the titration, right? So the Ka that you're going to determine for this thing is the HX floating around in water. The titration has not been done. It's not even a little glint in your eye yet. So it's just floating around doing what it does. And weak acids in water, they go to equilibrium. And at equilibrium, you have all these different concentrations. So at equilibrium, you will have a certain amount. They're not all going to be the same, but you will have a certain amount on each of those lines. And if I'm going to calculate a Ka, which is what this question is asking me, if I'm going to calculate the Ka, I need a numerical value on each of those spaces. I need a number there, there, and there. Okay? So you have to understand, what does the titration tell you? What does the titration not tell you? That's critical as well. And then you can fill in based upon what you find out from the titration. And then once you have numbers, you actually have a numerical value on each of those spots. You can then put it into the K expression and go along and calculate the Ka. So what numbers do I know already? Do I know any numbers? Now, it's kind of tricky because we always use this wording, and the wording tends to mess people up, right? Because an IRE table has initial reaction or change, if you use the ICE, and equilibrium. That initial word tends to freak people out. This word right here, I said solution had a pH of 3.80. I intentionally did not use the word initial, but many times the problem will be stated, HX solution had an initial pH of 3.80. This is a semantics problem. This is a chronology issue here. When it said the solution of HX had an initial pH of 3.80, that means initial, meaning just before you did the titration, but already at equilibrium for HX solution. Okay, so you have to imagine kind of in the timeline or the lifetime of this solution of HX, the solution of HX got made. So some HX was dissolved into water and a solution was made. It rapidly went to equilibrium. Like it took it probably seconds to get to equilibrium. And so as soon as you made that stuff, it's at equilibrium. It's already done what it was typically doing. And that equilibrium would have made those numbers right there. And so the solution, before you even walked it over to your table to do the titration, had a concentration of HX, had a hydronium, and had an X minus concentration. It had all of those things already. So when you're talking about the initial pH of the solution, you're actually talking about this solution at equilibrium, okay, when you're talking about its pH. So this value right here, that value right there is actually that number right there. It is the equilibrium concentration of the hydronium, meaning this is kind of what it's reading, okay? Now, if I knew that value, which of course pH, I can convert that into a concentration of hydronium, that value and that value are going to end up being the same, right? Because they both started at, and I'm going to fill this in a little bit more, they both start at 0, they both went up as soon as this thing formed equilibrium to the same value. This concentration would have gone down that same amount, okay? So there would have been an initial amount when we made the solution. It would have gone down a certain amount, and it would have ended up at something. So what I'm going to do is I'm going to go through the process of filling in what I can based on the pH, okay? So let's go through this, okay? And I've already got the numbers written down, so I don't have to pull out the calculator just quite yet. Okay, so this solution, we're not even talking the titration. Keep that in mind. We're not talking about the titration here. This is just this HX in solution. This guy started out 0 and 0. There was a certain value of HX concentration initially. It chemically reacted. It went up a certain amount. Now, how much did it go up? Oh, let's use the pH to figure that out. So, can we see it? Yeah, we can see it. So, the hydronium concentration equals 10 to the power of the negative pH, which is 10 to the power of negative 3.80 Okay, so you got to go back to the acid base, and you know at this point probably how to convert a pH back into a hydronium concentration. So the hydronium concentration, if you do that, 10 to the power of negative 3.80 comes out to 1.6 times 10 to the negative 4 molar. Okay, which means that the equilibrium number that's right there will be 1.6 times 10 to the negative 4 molar. I'm going to clear it out a little bit so we can see it a little bit easier. So, clear this out a bit, get rid of that blue circle. Okay, so this is 1.6 times 10 to the negative 4. Now let's use our stoichiometry and our logic here, which it started at 0 and it went up that amount. That means that the x minus did the exact same thing. So it also went up 1.6 times 10 to the negative 4. And at equilibrium was also 1.6 times 10 to the negative 4. Don't forget, though, that this guy over here, that R, would have gone down that same amount. So I haven't even contemplated the titration part of this question yet. What I've done is I've just taken this pH of 3.80 and I've said in my mind, okay, this is how much of the IRE table I can figure out before we even contemplated doing a titration. Now, the titration, what's the purpose of the titration? The purpose of the titration is to find out the concentration of that acid. So it's to fill in that one column that we don't know about, okay? Now, which value does a titration figure out? And that's critical. Titrations, it's kind of interesting because they kind of take you back in time. They take you back in time to try and determine how many moles of that acid did we originally dissolve into the solution. So it tells you, titration tells you that number. It tells you the initial concentration. So if you go back to many episodes ago now in the acid base unit, when I was showing you how do you calculate the Ka of a weak acid. And the question that I gave you in that scenario, it said an acid with an initial concentration of this, and I just gave you the number. Titration is how you got that number. And it will allow you to do that. Okay, so titration will take you back in time and say, okay, how many moles of that HX were originally dissolved into the water? It doesn't tell you this number down here, because what it does is it reacts away. Yeah, okay, it reacts all the molecules that are floating around at equilibrium, but as it's doing that, it's creating a Le Chatelier shift back from right to left. And so eventually all the moles that did react in the original equilibrium will come back to HXs. And so your titration will eventually get rid of all of them, even those that reacted in the very first place. Okay, so it's kind of a tricky little chronology that you have to get your brain to see. You can also just flat out memorize that a titration tells you that initial concentration, period. Okay, which is fine. So then we know that, okay, now we've got to do the titration calculation stuff to get to that part of the IRE table. So then we step over here and we take a look at our data that was given. Okay, so according to the data table, we took 10 milliliter samples of the unknown acid. Okay, so we did the pipetting thing, 10 mils. It gives you the initial reading and the final burette reading for the sodium hydroxide. 2 trials were done. This is where we started. This is where we finished for each one. The difference between those two will be how much base you actually added. So the very first step that you have to do is you have to figure out how much base did I use for each trial. Okay, so we started at 2.81, we finished at 16.89, so you subtract 2.81 from the 16.89, and you end up getting 14.9. milliliters of base added for trial number 1. Okay, trial number 2. 21.05 minus 7.09. Do that math, and you get 13.96 milliliters. So as you recall from the last video, neither one of those is correct. You're taking the average, right? So you do as many trials as you possibly can to get what you believe is the most accurate value for it. So if I did a third trial, the average would be supposedly even more accurate. 4 trials more accurate, so on and so on and so forth. So 2 trials fairly close together though. So we're going to go with the average of those 2. So the average volume equals 14.08 plus 13.96 divided by 2 equals, the difference is 12.6, 14.02 milliliters of base that was added. Okay? So that's the volume that we're going to then proceed with. So now we do moles of unknown, or sorry, not moles of unknown, the moles of the base that were added. So the moles of NaOH equals, okay, well, where am I here? I'm 0.150 moles per liter times 0.01402 liters. Got to convert it to liters because you have to cancel the liters. Okay, so there's 1,000 mils. Move the decimal 3 places to the left. Okay, yada yada. We do the math, and when you do the math, okay, so I haven't done this one. So 0.15 times 0.01402 equals 3 sig figs, 2.10 times 10 to the negative 3. Not molar, sorry, moles. So that's the moles of our base. And once we've done the moles of our base, then we can use the neutralization equation to figure out the moles of our acid. Okay, so we need a neutralization equation. So we can't just, at least I don't allow people to kind of miss that stoichiometry of the neutralization equation. You have to communicate to me why you know they're the same value. So the next step would be, okay, I know the moles of the NaOH. That's the good one. How do I know the moles of the unknown acid? Well, the equation would be, always got to have a neutralization equation. We took some aqueous NaOH. We took some aqueous HX. It reacted 100% to form water and NaX, and the X must have been a -1 because it had one H on it. Okay, so the ratio is 1 to 1. Therefore, moles of HX have to equal the moles of NaOH, which equals 2.10 times 10 to the negative 3. Right? So you're just communicating it using a neutralization equation to prove that you know how many moles we're talking about here. Okay, so that's just being fully communicative with your teacher. Okay, so now we need the concentration, because we can't put moles in here, we need a concentration. So the molarity, and you might even want to write, so you do the little square brackets around the HX to indicate concentration of HX. You might want to put a little I, indicating this is the initial concentration of the HX, is 2.10 times 10 to the negative 3 moles divided by 0.0100 liters. Keep the sig figs, keep the zeros to indicate, sig figs and remind yourself, which means the acid was 0.210 molar. Okay, so, but we're not done yet. What that tells me is it tells me that this goes right there. Okay, that's all it tells me, is that it goes right here. 0.210 on the initial line. That's what it does. Okay, so now we're like super close to being able to actually fill in the K expression and go ahead and do the calculation. Okay, now don't just make the assumption that that subtraction isn't like the 0.210 is going to be 0.210 down there. That's not a good assumption to make because we're usually talking about fairly precise values here. So if I go 0.21 minus 0.00016, it actually changes it. It actually doesn't change it. It actually stays as a 0.210. Okay, so it's actually 0.2098. That 8 means the 9 has to round up. Okay, so in fact, 0.210, it didn't actually have a significant effect on it. Now, you might say, well, why were you making such a big deal about this? When you do a titration, you're getting the initial concentration and not the equilibrium concentration, because it's not always the same value. So you have to be very careful. Sometimes this subtraction is actually significant. So you can't just ignore it and move on. Okay, so it can be the same as we just saw, but it's not necessarily the same. So now what do we do to actually do the Ka? So now what we would have to do is now, and I've kind of run out of room on my board, wherever your page is, down below, you'd write a K expression, plug in the values, and get the K. So I'm going to erase, and then I'm going to fill that stuff in. Okay? So this equilibrium, what we're doing is we're now going to, okay, I've got the IRE filled in. I'm talking about this equilibrium. This is almost as if the titration was never done. So the titration is kind of this little side event to find that number. And then we can pretend the titration never happened. Okay, just poof, disappeared. And so now we've got a filled in IRE table. Now you just revert back to just doing a weak acid calculation. So the Ka of this thing will be the hydronium times the X minus over the HX. And we're talking all equilibrium values, right? So the Ka will be 1.6 times 10 to the negative 4 times 1.6 times 10 to the negative 4. Of course, you could have just written that squared over 0.210, which I get 2 sig figs. So 1.6 times 10 to the negative 4 squared. Divided by 0.21 equals, and I get 1.2 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. And there's my value of Ka. Okay, so it keeps fading to black on me here. So once you've got that value, now you could have been asked a couple of different questions. So let's pretend this was being done at 25 degrees and you get a value of that, and you know it's a weak monoprotic acid. Well, if you had a table of Kas at 25 degrees, you could then find the weak monoprotic acids that are in that neighborhood, and hopefully, I mean, if it's a question that's kind of been made up on a test or something, it'll probably match perfectly because the teacher will make the numbers match perfectly. You can actually identify using the Ka. As long as you know the temperature, you can do that, okay? So it's an identifying feature, is the Ka. And that's how you go about doing it. So a couple of things to remind you here is when you take the pH of a solution, you're kind of taking the pH, or you're figuring out the hydronium of that thing while it's sitting there doing its own equilibrium. A titration will tell you the initial acid concentration. It always gives you that number right there. Remember that. That's what it's doing. So you do the titration calculation kind of over on the side to get the initial acid concentration, and then once you've got it, poof, it's gone. You plug that value into the IRE table, into the original equilibrium, and you work your way through, and you get the Ka using that calculation. Okay? So kind of understand what the purpose of the titration is for that type of a calculation. Okay, question number 2. I've got to do a bit of erasing here. Okay, so question number 2. It's going to be a percent purity question. So one of the assumptions is that you know what percent purity means. And so percent purity means the percentage that's given to you is referring to how much of a reactant, pure reactant, is mixed into this impure sample of it, which means there's impurities kind of mixed in there, adding mass to it. They don't chemically react in the way that the pure reactant will. So they just they don't do anything. They sit there and they're contributing mass, but they don't do anything. Okay, it's almost as if I had this kind of giant chunk of chemical and it was, say, only 90% pure. That means 90% of that part down there, and I mean, usually it's not divided so obviously, but 90% of that chunk is the actual chemical we're talking about, and 10% is, that chunk up there, would be 10% of the mass would be impurities, things that won't react, they're not doing what you expect them to do, they're just mixed in. Now, of course, if you're talking about an actual impure sample, chances are that 10% is kind of mixed in kind of all over the place, but it still won't react, right? So you'll do a chemical reaction, the 90% will react, and then the 10% will float around in the water or wherever, it's just completely unreacted, okay? Okay, so that's kind of the general principle here. So the question that I'm going to give is this. So a 0.960 gram impure sample of Na2CO3 is titrated with 0.320 molar HCl to determine its percent purity. Okay, so that's kind of a little bit of a descriptor of what the scenario is. So you've got this 0.960 chunk or powder or whatever, and it's impure Na2CO3. So right off the bat, you do not know of the 0.960 grams, you don't know how much of that mass is actually Na2CO3. The titration that you're going to do will tell you how much is actually Na2CO3. The percent purity will be that amount divided by the 0.960, and that will give you the percent purity, okay? So that's kind of our overall strategy. So in this case, you were told how the titration was being done. We're titrating using 0.320 HCl, which is a strong acid, which means the Na2CO3 is a base, okay? Strong, we can figure that one out here just in a sec. Na2CO3 it's a basic salt, which means when you dissolve it into water, the Na plus ions are spectators. They're not acting as an acid, not acting as a base. The CO3 negative 2 ions will act as a base, which means they're a perfect they're a perfect chemical for HCl to do a neutralization reaction with to determine its concentration. So that's kind of the strategy of the chemist in this one. Is you've got Na2CO3, it's a base. Let's titrate it with HCl and let's see how much CO3 negative 2 we have in there. And from that amount, we'll be able to tell how much Na2CO3 was in the original sample. That's our overall strategy. Okay, so let me kind of finish off how much we had here. If it took uh, 54.38 milliliters of HCl to reach the end point, what is the percent purity of the sample? Okay, so I'm not giving you a data table. We're not doing multiple trials. We're not having to average anything. It's just kind of, it's flat out telling you what we did. We did one trial. We took some HCl. We added it into the Na2CO3. It took this much HCl. That's enough info. Let's go for it. Okay, so how do we go about doing this? So we don't have a data table, so we don't have to do any averages. We don't have to subtract. We don't have any of that. We've kind of already cut to the chase on that one, right? So that 54.38 milliliters of HCl is already kind of the average, or if like if 4 trials were done and this is the average, right? So we're already at that stage. So what I'm going to do is I'm going to kind of cut to the chase and say how many moles of HCl were used. So moles of HCl equals concentration times volume. So the concentration of the acid, the HCl is right there, so it's 0.32. 0.320, keep the 0 because it's a sig fig, times the volume, change to liters, so move the decimal 3 places over. So there's the volume of the HCl, so times 0.05438 liters, liters cancel, and I end up with 0.32 times 0.05438 equals 0.01736 sig figs, 74 moles. Okay, so that's how much HCl we used to do the titration. So what was the neutralization equation here? So it was HCl plus, okay, now whatever one you choose, you can either choose CO3 negative 2, which is the actual base that is being titrated, and that's fine, you can do that. Or you can use the chemical that's given in the question, okay? So the formula equation of the ionic compound that you ended up being the actual base. So I'm going to do that one. I'm going to throw in the Na2CO3. Now, you do the titration, which means you would have had to make a solution out of that thing. The volume, because I'm not asking you about concentration, right? So how much distilled water you use to dissolve the Na2CO3 doesn't matter. Just enough to make sure that it's fully dissolved, right? So you have to sometimes just think logically in your titration. Does the volume matter? Does the concentration matter at this point? And so if you measured 0.960 grams of the Na2CO3, that was obviously on a scale. You threw it into a beaker and you threw in some water to dissolve it so you could do the titration. How much water you threw in doesn't matter. No one asked you for the concentration of the Na2CO3. You already knew the mass, which means the moles of the Na2CO3, they're going to be in that sample. right? So the amount of water you add is not really important. So I'm using this. It goes 100% because of the HCl. Now, what does it make? And so, again, I think I said this last video, it's kind of helpful almost to be thinking almost science, 10 double displacement swap partners. So the Na drops the CO3 negative 2 and picks up the Cl minus from the HCl. So Na is going to form a compound. I'm going to write it over here. It'll form NaCl. And then that means the H from the HCl and the CO3 negative 2 are going to form the product, or one of the products. And so that will form H2CO3. And it's H2CO3 because CO3 has a charge of negative 2. And therefore it's going to take two H's to go on to that negative 2. So truly, the CO3 negative 2 is the actual base. The sodium is just a spectator. It's a spectator over here, right? There's two Na pluses over here. There's an Na plus over here. Really, the Nas aren't paying attention to what's going on here. They're not involved. They're floating around, whatever. Okay? But I'm just keeping them in there because that was part of the original compound that we're talking about. Okay? So now it's not balanced. So I've got two Nas over here, and I've got one there. So I need a 2 there. That means there's 2 chlorides, which means I need a 2 in front of there. So we need a balanced neutralization equation. So we know the moles of our HCl, and what we're looking for is we're looking for the moles of the Na2CO3. So I need moles of Na2CO3. Equals. So we got to use our stoichiometry, and it's not 1-to-1 ratio here. So I need to use the stoichiometry. So do I multiply by 2 or do I divide by 2? And my little saying that I use with begin with my Chem 11s, and then I teach it again in Chem 12 if I didn't teach some of those people. I try and get this little saying into their head. The moles of what you want equals the coefficient of what you want over the coefficient of what you have. So you have the moles of the HCl. That's what you have. So coefficient of what you want is the Na2CO3. So the coefficient of what you want is right there, the 1, over coefficient of what you have. Well, I have the moles of the HCl, which is the 2. So it's over 2. Times the moles of what you have, times the moles of HCl. So I'm going to take 1/2 times 0.0174 moles. Okay, so I'm going to take that and I'm going to divide it by 2, and that's going to be my moles of Na2CO3. So that is 0.0087. Some of you may catch me on the Sig Fig Rule here. Really, when you're doing stoichiometry, the Sig Fig Rule should actually be the level of precision. So if you had a mole measuring machine and it measured it to 4 place values there, chances are you would only go to 4 place values there. But that's a very finicky little rule. Some teachers will follow that rule. Some teachers will have been taught or will have grown up with different rules. There's a lot of controversy there, so I'm not going to worry too much about it. I've got 3 sig figs there. I'm just going to keep 3 sig figs. So that's how many moles of Na2CO3 were in the sample. So to get the percent purity, I need to change that moles into a mass of Na2CO3. So the mass of Na2CO3 will be 0.00870 moles, and then I'm going to need the grams per mole, the molar mass of Na2CO3. So real quick over on the side, you do a little quick molar mass calculation. So I've got 2 times sodium. So sodium's 23.0 on the periodic table. So it's 46.0. I've got 1 carbon, which is 12. I've got 3 oxygens, which are 16 each, times 3 is 48. 106.0 grams per mole. So this is 106.0 grams per mole. Okay, so I go times 106, and I get 0.922 Sig Figs grams. Okay, so that's how many grams of Na2CO3 were actually in there, and the titration is telling me that because of how much control I have, right? So controlling it so that you added exactly 54.38 mils, that's kind of critical, right? So you get this very precise value down here. Now the percent composition is, so the impure sample was 0.960 grams. Of that 0.960 grams, 0.922 of it was pure Na2CO3. The remaining, what is that, 0.038 grams, so not very much, is impure whatever. Who knows what it is, right? No one ever cares. It's not reacting with the HCl. So the percent purity will be 0.922 grams divided by 0.960 grams. And we're going to move the decimal 2 places to the right because it's a percentage. Notice that the grams cancel, right? The units cancel, so you end up with a percentage that's a unitless value. So 0.922 divided by 0.96 equals 96, and I get 3 sig figs, so 96.0% pure. 96% pure. Okay, and titration is a very useful tool this way because because it's so controlled, you can add a very specific amount of reactant, and you'll know when the whole thing's done because you've got your indicator in there, you've thought about where the equivalence pH should be, and you'll stop at a very precise level, and so you'll know quite well. So, and this technique is used quite often out there in the chemistry world when they're trying to determine the percent purity of different things that are out there. Titration is oftentimes used. One of the tricky things is that you got to make sure that what you're titrating with, HCl in this case, does not react with the impurities. Because if it reacts with the impurities, then it messes up how much HCl did it require to get to it, which is a little bit of the tricky part of it all. Okay, so there are a couple of very practical things that you can be doing with titration. So if you're ever asked those situations in labs or in test situation or homework or whatever you're asked, hopefully I've kind of guided you through with some important steps that you can use to get to that stage where you'll be able to do those calculations with no problem. Okay, next class, what I'm going to do is I'm going to continue with a couple of things. One I'm going to do is determining whether something is a weak or strong acid. That one will go pretty quickly. And then another one that we're going to do is percent ionization. And then beyond that, the last class that we're going to do for titration, we are going to do the titration curves. So the graphs, if you had a pH meter and you're measuring pH at, say, every milliliter as you're going through a titration, you'll actually visualize the changes in the pH as the pH is going on. And different combinations will give you very distinct graphs. And so one of the things you're expected to know in Chemistry 12 is the identifying features of those graphs and what have you got? What are you actually titrating if you see this type of a graph? Okay? And then we'll be done titration. We'll be into the last unit of reduction oxidation. Okay? So we'll see you next time. A couple more little titration problems, then we'll be moving on into the graphs. Okay. See you later.